Welcome to the fascinating world of nuclear physics, where we explore the very core of matter and the forces that hold it together. Nuclear physics is a branch of science that studies the components and behavior of atomic nuclei. This field has revolutionized our understanding of the universe, from the smallest particles to the immense energy released in nuclear reactions. In this video, we'll journey through the basics of nuclear structure, the discovery of radioactivity, and the profound impact these phenomena have on our daily lives. Let's begin by understanding what makes up the nucleus and why it's so important. The heart of every atom lies the nucleus, a dense region composed of protons and neutrons. Surrounding the nucleus are electrons, which orbit in defined energy levels. The nucleus is incredibly small compared to the entire atom, yet it contains almost all the atom's mass. Understanding the structure of the atom is crucial, as it forms the foundation for nuclear physics. The arrangement and number of protons and neutrons determine the identity and stability of each element. This structure also explains why some atoms are stable, while others are prone to radioactive decay. Discovery of the atomic nucleus was a groundbreaking moment in science. In 1911, Ernest Rutherford conducted his famous gold foil experiment, which revealed that atoms have a tiny dense center. When alpha particles were fired at thin gold foil, most passed through but some bounced back, indicating a concentrated positive charge. This led to the realization that the nucleus exists and is responsible for most of the atom's mass. Rutherford's work laid the foundation for modern nuclear physics and opened the door to exploring the forces within the nucleus. Inside the nucleus, protons and neutrons are held together by the strong nuclear force, one of the four fundamental forces of nature. This force is incredibly powerful but acts only over very short distances. It overcomes the repulsive electromagnetic force between positively charged protons, ensuring the nucleus stays intact. However, if the balance between these forces is disrupted, the nucleus can become unstable, leading to radioactive decay. Understanding these forces is essential for grasping why certain elements are radioactive and how nuclear reactions occur. Radioactivity is the process by which unstable atomic nuclei lose energy by emitting radiation. This phenomenon was first discovered by Henry Becquerel in 1896, and later studied by Marie and Pierre Curie. Radioactive decay can release alpha particles, beta particles, or gamma rays, each with different properties and effects. Radioactivity is a natural process that occurs in many elements, and it plays a crucial role in both nature and technology. From medical treatments to energy production, radioactivity has far-reaching applications. There are three main types of radioactive decay: alpha, beta, and gamma. Alpha decay releases a helium nucleus, reducing the atomic number by 2. Beta decay involves the transformation of a neutron into a proton or vice versa, emitting an electron or positron. Gamma decay, on the other hand, emits high-energy photons without changing the number of protons or neutrons. Each type of decay has unique characteristics and effects on the nucleus, influencing the stability and identity of the resulting atom. Alpha decay occurs when an unstable nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons. This process decreases the atomic number by 2 and the mass number by 4, transforming the original atom into a different element. Alpha particles have low penetration power and can be stopped by a sheet of paper, but they are highly ionizing. Alpha decay is commonly observed in heavy elements like uranium and radium, playing a significant role in the natural decay chains found in the Earth's crust. Beta decay is a process where a neutron in the nucleus transforms into a proton or vice versa, emitting a beta particle. There are two types: beta-minus decay, where an electron is emitted, and beta-plus decay, where a positron is released. Beta particles have greater penetration power than alpha particles but are less ionizing. This type of decay changes the atomic number by 1, resulting in the formation of a new element. Beta decay is essential in many natural and artificial processes, including the functioning of nuclear reactors. Gamma decay involves the emission of gamma rays, which are high-energy photons, from an excited nucleus. Unlike alpha and beta decay, gamma decay does not change the number of protons or neutrons in the nucleus. Instead, it allows the nucleus to release excess energy and reach a more stable state. Gamma rays have very high penetration power and can pass through most materials, making them both useful and potentially hazardous. They are widely used in medical imaging and cancer treatment due to their ability to target specific tissues. Half-life of a radioactive substance is the time it takes for half of its atoms to decay. This concept is fundamental in nuclear physics, as it helps scientists predict how long a radioactive material will remain active. Half-lives can range from fractions of a second to millions of years, depending on the isotope. Understanding half-life is crucial for applications like radiometric dating, nuclear medicine, and managing radioactive waste. It provides a predictable way to measure the stability and longevity of radioactive materials. Isotopes are atoms of the same element with different numbers of neutrons. Some isotopes are stable, while others are radioactive, meaning they decay over time. Radioactive isotopes, or radioisotopes, have a wide range of uses in science, medicine, and industry. For example, carbon-14 is used in dating ancient artifacts, while iodine-131 is used in treating thyroid disorders. The unique properties of each isotope determine its applications and safety consideration. Radioactivity is not just a man-made phenomenon. It occurs naturally all around us. The Earth's crust contains radioactive elements like uranium, thorium, and radon. Cosmic rays from space also contribute to natural background radiation. Even our own bodies contain small amounts of radioactive isotopes, such as potassium-40. Understanding natural sources of radioactivity helps us appreciate the balance between exposure and safety in our environment. Artificial radioactivity is created when stable elements are transformed into radioactive ones through nuclear reactions. This process was first discovered by Iron and Frédéric Joliot-Curie in the 1930s. Artificial radioisotopes are produced in nuclear reactors and particle accelerators for use in medicine, industry, and research. These man-made isotopes have revolutionized fields like cancer treatment, medical imaging, and industrial testing, providing tools that were previously unimaginable. Nuclear fission is a process where a heavy nucleus splits into two smaller nuclei, releasing a tremendous amount of energy. This reaction is the principle behind nuclear power plants and atomic bombs. When a nucleus like uranium-235 absorbs a neutron, it becomes unstable and splits, releasing more neutrons and energy. These neutrons can trigger further fission reactions, creating a chain reaction. Fission provides a powerful source of energy, but also presents significant safety and environmental challenges. Nuclear fusion is the process where two light nuclei combine to form a heavier nucleus, releasing energy in the process. Fusion is the reaction that powers the sun and other stars, producing vast amounts of energy from hydrogen atoms. Unlike fission, fusion produces little radioactive waste and has the potential to provide clean, limitless energy. However, achieving controlled fusion on Earth is extremely challenging due to the high temperatures and pressures required. Nuclear physics has countless applications that impact our daily lives. In medicine, radioactive isotopes are used for imaging, diagnosis, and treatment of diseases like cancer. In industry, they help inspect materials and control processes. Nuclear power plants generate electricity for millions of homes. Even in archaeology, nuclear techniques like radiocarbon dating help us understand the past. The versatility of nuclear physics continues to drive innovation across many fields. Nuclear medicine uses radioactive substances to diagnose and treat diseases. Techniques like PET scans and radioactive tracers allow doctors to visualize internal organs and detect abnormalities. Radioisotopes can also target and destroy cancer cells with minimal damage to healthy tissue. The safety and effectiveness of nuclear medicine rely on precise control of radiation doses and careful selection of isotopes. This field has transformed healthcare, offering new hope for patients worldwide. Nuclear power plants use controlled fission reactions to generate electricity. Uranium or plutonium fuel rods are placed in a reactor where they undergo fission, releasing heat. This heat is used to produce steam, which drives turbines and generates electricity. Nuclear power is a low-carbon energy source, but it requires strict safety measures to prevent accidents and manage radioactive waste. The debate over nuclear energy continues, balancing its benefits and risks. Nuclear weapons harness the immense energy of fission or fusion reactions to create devastating explosions. The first atomic bombs were developed during World War II, forever changing the course of history. The destructive power of nuclear weapons has led to global efforts to control their spread and prevent their use. Understanding the science behind these weapons is essential for promoting peace and security in the modern world. Radiation safety is a critical aspect of working with nuclear materials. Exposure to high levels of radiation can cause serious health effects, including radiation sickness and increased cancer risk. Protective measures include shielding, limiting exposure time, and maintaining distance from radioactive sources. Regulatory agencies set strict guidelines to ensure the safety of workers and the public. Understanding and respecting these precautions is essential for anyone involved in nuclear activities. Radiation is measured using specialized instruments like Geiger counters and scintillation detectors. These devices detect and quantify the amount of radiation present in an environment or emitted by a material. Units such as becquerels, grays, and sieverts are used to describe radioactivity, absorbed dose, and biological effect, respectively. Accurate measurement is essential for ensuring safety, conducting research, and monitoring environmental radiation level. Radiation is a natural part of our environment. We are exposed to background radiation from the ground, the air, and even the food we eat. Everyday items like smoke detectors and luminous watches also contain small amounts of radioactive material. While most exposure is harmless, understanding the sources and effects of radiation helps us make informed decisions about safety and health. Radiocarbon dating is a technique used to determine the age of ancient objects by measuring the amount of carbon-14 they contain. Living organisms constantly absorb carbon-14, but when they die, the isotope begins to decay. By comparing the remaining carbon-14 to stable carbon, scientists can estimate how long ago the organism lived. This method has revolutionized archaeology and paleontology, providing accurate timelines for historical events. Nuclear reactors are devices designed to maintain controlled nuclear fission reactions. They use fuel rods, moderators, and control rods to regulate the reaction and produce heat. This heat is then converted into electricity. Reactors come in various designs, each with unique safety features and efficiency levels. The operation of nuclear reactors requires careful monitoring and strict adherence to safety protocol. Managing nuclear waste is one of the biggest challenges in the nuclear industry. Radioactive waste must be safely stored and isolated from the environment for thousands of years. Methods include deep geological repositories, secure containers, and reprocessing to extract usable materials. Effective waste management ensures the long-term safety of people and the planet, and it's a critical part of any nuclear program. Nuclear accidents, though rare, can have severe consequences for people and the environment. Famous incidents like Chernobyl and Fukushima highlight the importance of safety and preparedness. Causes can include equipment failure, human error, or natural disasters. Learning from these events has led to improved reactor designs, stricter regulations, and better emergency response plans. Use of nuclear energy is a topic of ongoing debate. Supporters argue that it provides reliable, low-carbon electricity and can help combat climate change. Critics point to the risks of accidents, waste disposal, and high costs. As technology advances, finding a balance between benefits and risks remains a key challenge for policymakers and the public. Nuclear physics plays a vital role in space exploration. Radioisotope thermoelectric generators power spacecraft on long missions, while nuclear reactions help us understand the life cycles of stars. Studying cosmic rays and nuclear processes in space expands our knowledge of the universe and the origins of matter. Particle accelerators are powerful machines that speed up atomic particles to high energies and smash them together. These collisions allow scientists to probe the structure of matter and discover new particles. Accelerators have led to major breakthroughs in physics, including the discovery of the Higgs boson. They also have practical uses in medicine and industry. Standard model is a theory that describes the fundamental particles and forces in the universe, except gravity. It includes particles like quarks, leptons, and bosons, and explains how they interact through the strong, weak, and electromagnetic forces. The Standard Model has been confirmed by countless experiments, but mysteries like dark matter and gravity remain unsolved. Neutrinos are tiny, nearly massless particles that rarely interact with matter. Trillions pass through your body every second without leaving a trace. They are produced in nuclear reactions, such as those in the sun and nuclear reactors. Studying neutrinos helps scientists understand fundamental processes in the universe and may reveal new physics beyond the Standard Model. Quarks are the building blocks of protons and neutrons, while gluons are the particles that hold quarks together through the strong force. There are 6 types of quarks, but only 2 up and down make up ordinary matter. The study of quarks and gluons is at the frontier of nuclear and particle physics, deepening our understanding of the universe's most basic components. Antimatter is made of particles that are the mirror image of ordinary matter. When matter and antimatter meet, they annihilate each other, releasing energy. Antimatter is rare in the universe, but it is produced in particle accelerators and certain types of radioactive decay. Understanding antimatter could unlock new sources of energy and answer fundamental questions about the universe. Beyond imaging and cancer treatment, nuclear physics contributes to medicine in many ways. Radioisotopes are used to sterilize medical equipment, trace biological pathways, and study metabolic processes. Advances in nuclear techniques continue to improve diagnostics and therapies, making healthcare safer and more effective for everyone. Industry relies on nuclear physics for a variety of applications. Radioisotopes are used to inspect welds, measure material thickness, and detect leaks in pipelines. These techniques are non-destructive and highly accurate, improving safety and efficiency in manufacturing and construction. The use of nuclear technology in industry continues to expand as new methods are developed. Nuclear activities can impact the environment through radioactive waste, accidents, and thermal pollution. Careful management and strict regulations are essential to minimize risks. Advances in technology are helping to reduce the environmental footprint of nuclear power and improve waste disposal methods, making nuclear energy a more sustainable option for the future. Research in nuclear physics is ongoing, with scientists exploring new isotopes, reactions, and applications. International collaborations and advanced facilities drive discoveries that expand our knowledge of matter and energy. The quest to understand the nucleus continues to inspire innovation and push the boundaries of science. Future of nuclear energy lies in developing safer, more efficient reactors and harnessing fusion power. Innovations like small modular reactors and advanced fuel cycles promise to make nuclear energy more accessible and sustainable. Continued research and investment are key to realizing the full potential of nuclear technology in meeting global energy needs. Nuclear physics has shaped society in profound ways, from powering cities to advancing medicine and deepening our understanding of the universe. It also raises important ethical and safety questions. As we continue to explore the nucleus, it's essential to balance innovation with responsibility, ensuring that nuclear technology benefits humanity while minimizing risks. Many brilliant minds have contributed to the field of nuclear physics. Pioneers like Marie Curie, Ernest Rutherford, Niels Bohr, and Enrico Fermi made groundbreaking discoveries that changed science forever. Their work laid the foundation for modern nuclear research and continues to inspire new generations of scientists. Women have played a vital role in the advancement of nuclear physics. Marie Curie's pioneering research on radioactivity earned her 2 Nobel Prizes. Today, women continue to make significant contributions in research, education, and industry, breaking barriers and inspiring future scientists. Development and use of nuclear technology raise important ethical questions. Issues like nuclear weapons, waste disposal, and environmental impact require careful consideration and responsible decision-making. Public engagement and transparent policies are essential for ensuring that nuclear technology is used safely and ethically. Teaching nuclear physics helps students develop critical thinking and problem-solving skills. Hands-on experiments, simulations, and real-world examples make complex concepts accessible and engaging. Education in nuclear science prepares the next generation to tackle global challenges and drive innovation in technology and healthcare. Career in nuclear physics offers exciting opportunities in research, medicine, energy, and industry. Nuclear physicists work in universities, laboratories, hospitals, and power plants, contributing to advancements that benefit society. The field demands curiosity, analytical skills, and a commitment to safety and innovation. Nuclear physics and radioactivity have transformed our world, unlocking new sources of energy, advancing medicine, and deepening our understanding of nature. As we look to the future, the responsible use of nuclear technology will be essential for addressing global challenges and improving quality of life. By continuing to explore the mysteries of the nucleus, we can harness its power for the benefit of all.